What are we looking at, 16? 16? Is that what you said? Oops, let's see what we got here. All right, so we got an open pipe. Well, this is a foreign, this is made in China. It's open to both ends. So, we've got a 2.5 meter, this is the fundamental wavelength. So for an open pipe, it looks like this. Oops. That's terrible. How much of a wave is in there for an open pipe on the fundamental? This is 1/2 wavelength, right? For the fundamental. So that a 1/2 a wavelength then, if that's the fundamental, that's got to be the 2.5 meters. That wavelength should be 5 meters, shouldn't it? No, this would be correct, because if this is the wavelength, 1/2 of that wave is going to be in the pipe, right? 1/2 of that wave. Okay, what else do we have? Steel wire on a piano, okay. So this will give you the mass per unit length, right? This would be the mass per unit length. Make sure you change this to kilograms. So that's your mass, that's your length. Then we have velocity is equal to, I have it on, oh, I'm blanking out on that. Bless it. Now, your book used this. Your book used FL over M square root, right? I have a couple questions on this. This is what we have. And that's the same thing. So, to what tension must the wire be stretched? Then that's going to be the force. So you're going to square both sides. If this is the speed, we can square both sides and solve for F. Yeah, because you're going to have to square both sides. You're going to end up with V squared is equal to FL over M, right? Because the square root of the square root, or the square of the square root, we get rid of that. Yep. Anything else? 6? Okay. "333 meters per second, the speed of light is 3 times 10 to the 8th meters per second. You see, let's see, the lightning flash, how long? Okay, 1 kilometer away. Do we need to even figure out how long it takes for the lightning flash to get to you, or for you to see it? We don't need to calculate that, right? We need to calculate this right here. This would be 1,000 meters. So if it's 1,000 meters away and it travels at 333, You know, I'd have to actually Google it. I don't remember. What a, there is a rule to it. What did Google say, Carrie? 1 mile is 5 seconds. Okay, so this should be 3 seconds, huh? For light, $11. Are we doing 11 now? All right. So a piano string. This is the mass per unit length right here. So the mass per unit length, this is the force. So for your length, for this length, put in 1 meter. Right? 0.005 kilograms for your length, 1 meter. That'll work. All right, anything else? What? 4? Let me look at 4. Oh, the equation online, or the problem online. What do you mean? The equation's right here. Right here's the equation. Did we update this sheet? Is this your... Is this updated? This, you guys put this in? Double check if you have this in. I thought we did this for the... I'm double checking all my classes. We put this in, right? All right, so let's add this. This is on page... Let's make sure we got this. Let's update this then. So this is... Yes, right here. So above 15, let's put this in. One over 2 pi, right here. I don't think that's that bad. What? You think that's that bad? So we cross this out. Right here's the equation for number 4. L is length, yes. G is gravity, yep. Yes. I crossed those out. We didn't use those. Did we cross this out? We didn't use these. This is the equation we've been using for sound. Here's your velocity on a string one. We'll use this, right? And this is what we've been using. Instead of this square root of t over 273, we've been using 0.6 times degrees Celsius. Yeah, if you want, you can cross this off. This right here is area. Area. Yep. This is intensity is equal to pressure divided by area. Yep. That should get us where we're at. Okay, let's bubble this on Monday then. We got to do some rotational motion here. You know what? I think we're just going to do that maybe like Tuesday, the last second of lab or something. We'll work on it together or something. Yeah, lab day, we're going to work on, I think, like maybe a 10-question thing. Okay. Let's talk about something rotating in a circle now. So we're going to talk about rotation, rotational stuff. Torque is really rotational force. But we need to get some background first. If you want a distance for rotation, our equivalent of distance in rotation is going to be whatever angle we sweep, right? Whatever angle we sweep. If we go all the way around this thing, we really do circumference. This would be L, or in our case, if it's circumference, what distance do we do if we go all the way around? What's the circumference of a circle? Our circumference of our circle would be 2 pi r, right? Yes. Yep. Best I could do for that. If we went all the way around, it would be 2 pi r. So this is my L again. It doesn't look like an L. But if I expanded on this, if L is equal to 2 pi r, then all the way around is going to be 2 pi r divided by this r. My r's cancel out. The book uses big R. I'm using little r. Same thing. So if you go all the way around once, that's 2 pi radians, right? All the way around once, 2 pi radians. Well, we know that that's 360 degrees to go all the way around. So 360 divided by 2 pi, 1 radian would be 57.3 degrees. Now, no. If you just looked at if you just said, okay, I have a wheel. How fast is it going for a velocity? If you just wanted to do the regular velocity that we've done, the distance would be 2 pi r, right? That's going to give you meters. That would give you meters per second, wouldn't it? At that radius. right? This would be meters per second. The other way could be 2 pi r divided by the period. Wouldn't that be meters per second? So that would be something that you could, what's that? No. If you just said, what's the linear motion of that? So now, here's what I want to do. I want to go down to the bottom. I want to do this chart at the bottom here. Then I'm going to come up and we're going to look at all of this. So this is going to be review. We're going to make a little chart here. Translational motion. Yep. Rotational motion. And relationship. Here we go. We need 1, 2, 3. Translational is just straight line. Straight line motion. We used X, right? Straight line motion, we used X. What's the unit we used? What's the unit we used? Meters, right? For velocity, what would be my units? Meters per second. And for acceleration, what would be my units? Meters per second squared. Okay. My rotational equivalent to distance will be that would be a distance, right? I swept out so many radians for a distance. My velocity then, it looks like this. It's a W, it's a swooping W. And if this is in radians, then rotational velocity is going to be how many radians per second you are sweeping. And the rotational equivalent of acceleration is alpha, and that would be radians per second squared. It would be radians per second squared divided by time to figure out how fast. Okay, so here's our relationship. I'm going to put it this way. If you want your distance, it's a radius times radians. Now here's how you can figure this out. These radians are really dimensionless units. Do my units match? If I don't consider radians a unit, this would typically be in radians. We're going to write radians. Do I have meters equal meters for units, right? This would be in meters. That's what you want to do. Just make sure your units work out. Your book might present it like this. Same thing, right? X over R. Now here I want to get meters per second. So this is going to be R omega. Yeah, it would look like this. But this is going to get you, this is in radians per second, right? This is in radians per second. This R would be in meters. So you get meters per second on both sides. And for here, our acceleration is going to be r alpha. Because what units is this in? Radians per second squared. So this would give us meters per second squared. Okay. Now, all of our previous equations are valid, which means this, I'll come back. But let's look at this chart. This says comparison of linear and angular accelerations. This, of course, is all linear. These are the equations that we used previously, right? All I'm substituting then, back and forth, distance in rotation is going to be radians, right? Velocity is going to be in radians per second. We're using all the same equations. This is distance again. We're just substituting in the rotational equivalents. It would be distance traveled, because displacement in a circle would not work, because it just wouldn't work. But all of these equations work then, right? This is V final equals V initial plus 2AX. This is velocity final in rotation equals velocity initial plus 2 alpha theta. And we'll do example problems like this, and we'll be using those. So if I go back to the beginning here to page 1, this is just saying that we would have theta 1 and theta 2. We have some change in theta along this arc, right? That change in theta is going to be in rotational velocity in radians per second. That is linear velocity. This is angular velocity. Then, remember, acceleration is v final minus v initial divided by time, correct? That is linear acceleration. Well, angular acceleration is going to be omega final minus omega initial divided by time. It is the same thing. We're just substituting in rotational equivalents, which then make all of our equations here exactly valid and exactly the same. Okay, let's try a problem here. And I'm still working on this as a work in progress. So we'll do a problem here. And I had to put the vinyl record on here because, I don't know, they're back, I guess. Everything comes back. Even those ugly Converse shoes, which I can't believe people wear. What? My stepdaughter has, I don't know how many of those stupid looking Converse shoes that, what a marketing genius. Whoever decided to come back, oh, we're going to make Converse big again. Those are, all right. So, this will be example 10.1, 347. Here's essentially the problem. We got a bike wheel from rest. Now, I got to ask this question, because it describes it like this. I guess I can freely admit, since I got the shingles vaccine, I'm 50 and over. I'm getting old. Here's how it describes the problem. A person takes their bike, sets it upside down, and turns the pedal. Have you all turned the bike upside down and turned the pedal? No. What's that? You don't like bikes? You can't. Do you have your driver's license? How did that go? No, I teach driver ed, right? So I get somebody in the car, and if they have, I had a girl one time. She didn't drive anything. I don't think she had a tricycle as a baby. I don't think she ever rode a bike. So she never judged distance when something is moving. Oh, it was a struggle. Oh. I grabbed the wheel a lot. Oh, it was a struggle.
Are you allowed to do that legally?
Yes.
Grab the steering wheel
Well, it's either hit a bridge at 50 miles an hour or grab the steering wheel. What are you going to do? Okay. So bike wheel from rest to 250 RPM in 5 seconds. We want to calculate the acceleration. Rotational acceleration. Rotational acceleration should be in what unit when we're all done? Radians per second squared, correct?
How do we know if it's asking for a linear in a circle or just
It will say linear in the wording. So let me ask you a question. What is my initial angular velocity? How many radians per second was it going initially? 0, right? Same thing from rest. So that hasn't changed, right? From rest. Now, it gets to 250 RPMs. So let's calculate omega final. Let's first do that. Because we're going to do acceleration with change in velocity divided by time. We just need to get omega final. We need to convert 250 RPMs to radians per second. So we can do that with, we've got 250, what's RPM stand for? Revolutions per minute. So I'm going to put revolutions down here. Then you'll use this conversion all the time. 1 revolution, 2 pi radians. So this gets omega final at 26.2 radians per second. So now everything's the same. We got omega final, right? This is omega final. This is my final angular velocity. So my angular acceleration is going to be omega final minus omega initial divided by time. So this is going to be 26.2 radians per second divided by 5 seconds. So this is going to be radians per second squared. And this is alpha. Now, in part B, it breaks at negative 87.3 radians per second squared. We need the time to stop. We'll put that right here because, like I said, this is a work in progress, and we're not doing 6.2, so let's put it down here. Time to stop. So, what is this for a unit? This is alpha, right? This is your acceleration, your deceleration, correct? This is alpha. So we know this is minus 87.3. We're looking for time. If we're coming to a stop, omega final is 0, right? What is omega initial? Omega initial is the 26.2 we calculated up here, correct? So now, let's see if we got all this on our formula sheet here. I think we do. Rotational motion, angular momentum. Not yet. Or, well, anyway, what equation could we use on here? Or you can use your other one, comparison. What are we trying to calculate? We're trying to get time, right? Yep. What equation do you want to use? We can use this one, which is the same as this one, right? We have omega final is 0. We have omega initial. We have our deceleration, correct? We need time, right? So this is the same equation we used before, where we used V final equals V initial plus AT. But this is omega final equals and if we're going to solve this for time, this is 0 minus omega initial divided by alpha would be our time, right? Yeah, omega comes to a stop, so this is 0. So I move this to the other side of the equal sign, so I put the negative there. And then I divide it by alpha. And if I plug this in, I am going to get minus 26.2 radians per second divided by negative 87.3. That's going to equal my time. My time is going to be what? 0.3. So that's kind of an introductory problem. Yeah, you should get the same thing because it, yeah, it's the same equation. You should get the same thing. Okay, here's 10.2. We're putting this up here by the record. What? You don't have room right here? Well, then put it down here. Yeah, put it right here then. Put your 10.2 right here in this area. It'll fit right here. We're not going to use that. Okay, so this is it doesn't focus on, if you got black on the outline, it doesn't focus on that black. Let's see what I use. No, that's radius. This is linear units, right? So let's get our linear acceleration first. We'll just do acceleration as v final minus v initial divided by t, right? Just like we did early on. Right? Nothing new here. This is why this is nice to do this towards the end. We're kind of reviewing everything a little bit, kind of. So if we just do this, we're going to end up with I think we're going to use that. Right now we're going to use that. Okay. Now, we then, remember we did this. We said that this is equal to R alpha, right? Think of this. This would be in radians per second squared, right? And don't think of radians as a unit. Then you'd have meters per second squared on both sides. That's how you check that you have the right equation. So then if we want the radial acceleration, it's our tangential regular acceleration divided by our radius, huh? Yes. So we would have 7.14 meters per second squared divided by 0.320 meters. Okay. Let's get, this one here I've got everything. Let's go to this that has the, meters are going to cancel out. So if the meters cancels out, you have to have radians per second squared. It's just, it's kind of, radians come up to be, what do they describe it as? Unitless. It's going to be in radians per second squared. It's like magic, I guess. Right, and we could go back and calculate, every circumference out of both of these to prove that out. Radians, otherwise you wouldn't have any top unit on this, right? You'd end up with just over seconds squared. So, yeah, you can just add the radians in as a unit. Add them in. It's like they describe it as a dimensionless unit. That's how they describe it. All right, let's do this problem. This will give you enough background. I've got one homework problem for you. All right, so we're not going to do this one anyway, but here's our hard disk drive. So Hutch, I don't even know if they're making these anymore. I'm assuming they are. So Hutch makes the readers for the hard drives. Anybody work at Hutch? No. So this is going to go up to 5,400 RPMs. What is the angular velocity of the disk? So we're just going to take this 5,400 RPMs and we are looking for omega, right? Angular velocity. Not linear, angular velocity. So this angular velocity is going to come out to be what units then? Radians per second, right? That's given for velocity. So this is revolutions per how many seconds? Then we'll use the same conversion, 1 revolution, 2 pi radians. This will give us units of radians per second, right? So this is sweeping out 565 radians per second. You could get degrees out of this. If a radius is 56.3 degrees, you could do how many degrees this is sweeping out, correct? You can change this to degrees, and then you could divide it by 360 to go how many times it's turning around per second? 2, correct? We could calculate that. Now, it says this: if the reading head of the drive is located 3 centimeters from the axis of rotation. Yes. Oh, not a question, you said. So if we say that this is out here at 3 centimeters, what is the speed of the disk below it? This is going to be in meters per second. And we are just going to simply use V is equal to R omega, because that'll get us meters per second, right? So we're going to use 0.03 meters, 565 radians per second. This is going to be about 17. Right, this is what we just calculated up above. Okay. Now, we're going to do D next. Start your computer up. This thing hums up to 5,400 RPMs. So if it hums up from rest on your started your computer, what's the acceleration? And this should be in radians per second squared, right? From rest then, omega initial equals 0, correct? So then we can do omega final minus omega initial divided by time. So omega final is 5,400 RPMs fixed once it reaches that speed. And we already have that up above at 565. The linear acceleration. Uh-oh. So 156? Sorry, so 157? 157. the linear acceleration. Then if we take 0.03 times our 157, what do we get?
So it's asking what the acceleration was before.
Correct. It would be good to switch those around. So what's 0.03 times 157? And this, since this is linear, oh, because I wrote the wrong thing down.
Yeah.
4.7 then? So this is going to be in meters per second squared. Still 4.7, right? Yeah, I just put the wrong symbol in there. All right, real quick on the last one. We're looking for how many revolutions did it take to come up to 5,400 RPMs. This will give us radians. So we're going to use this equation. This is our distance equation. This is our linear distance equation. So when this thing came up to speed, it started at 0. So we just have 1/2 alpha t squared.
So is that angle, that's the total amount of radians in the
We'll be able to calculate it. Just let me calculate it. This is going to be in radians, right? This should get us radians. So we get 1,017 radians. And then, how many radians in a revolution? 2 pi radians in 1 revolution. How many revolutions? Well, 117 divided by 2 divided by pi. What do we get? What'd you get? Did you square it? So it is 1,017? All right, 1,017 divided by 2 divided by pi. What do we get? 1,017 divided by 2 divided by pi. How many revolutions? 162. Okay, I want you to do this problem right here for homework. On the top of the next page. Do this right here for homework, this bicycle problem. Make sure you work on that. The bicycle problem be a good one.